Now question number 2. Find the extreme values of the following functions defined as. Before we move to parts of this question number 2, we will again recall the procedure to finding extreme values. And the procedure which we already discussed in our theory, and that procedure was the number of steps of that procedure was our first step was to find first derivative of the given function, and the second step was find second derivative, and then put this first derivative is equal to 0, and from this equation we will get the values of x for which this first derivative will be 0, and this one is actually our stationary points. So from here we will get the values of x, say c1, c2, etc., and named it to c. Let's see is the value which we get from this first derivative by putting it to 0. Next we will find, say this one is step 3. Now our fourth step will be find f double dash or second derivative at this x is equal to c, or we can say this one is f or f second derivative at x is equal to c. And if this second derivative at x is equal to c is greater than 0, then our given function, which is f of x, has relative minima. If f double dash c or a second derivative at x is equal to c is greater than 0, then our given function has relative minima. And if the second derivative at this c is less than 0, then the given function f of x has relative maxima, value when the second derivative is less than 0 at x is equal to c. But in some cases, if this double derivative at x is equal to c will become 0, then the second derivative test will not help in determining the values, or say extreme values. Then we can say our second derivative test will fail to determining the values or extreme values, and we will move towards our first derivative test and then check the point of inflection as we discussed in our theory. And that what is the point of inflection that is already discussed in our theory applications. Now we will move towards our question number 2 and repeat this procedure for every part and find the extreme values. Now our first part is f of x is equal to 1 minus x cube. We will find extreme values of this function by repeating or by applying that procedure which we already discussed. So first derivative of this function will be minus 3x square, as the derivative of 1 due to the constant function will be 0, and derivative of minus x cube will be minus 3x square. Then second derivative is minus 6x. By applying power rule on this function x square, which is derivative of x square will be 2x, multiplying to 3 will become minus 6x. Now for stationary points, put first derivative is equal to 0, and as first derivative was minus 3x square, so that will become equal to 0, and from here we can say x is equal to 0. The second derivative does not help in determining the extreme values. Why this happened? We can check or verify that when we put this x is equal to 0 in our second derivative, or we can say if f double dash or second derivative at x is equal to 0, that will become minus 6 into 0, which is 0. So that will not help in determining the extreme values. So we check our first derivative test. So before x is equal to 0, our first derivative is less than 0. That means if we put a value which is less than 0, say minus 1, and when we put this minus 1 into this minus 3x square, so being the square value, that will return a positive value. Multiplying to minus 3 will become a negative value. So first derivative will be less than 0 before x is equal to 0. And after x is equal to 0, which are a positive values, and when we put this value in minus 3x square, that will again be less than 0. So first derivative less than 0 before x is equal to 0, and also less than 0 after x is equal to 0, and that shows that will not changing the sign before and after x is equal to 0. Hence we can say x is equal to 0 has a point of inflection. So put x is equal to 0 in a given function f of x is equal to 1 minus x cube. F of 0 will become 1. Hence we can say point of inflection is 0, 1. This one is point, and this one is the value of x, and this one is value of y. This y coordinate, and that is actually a value of y. So the point of inflection is 0, 1. Again, we can repeat this procedure. When we have a function, we first find first derivative, then second derivative, and for stationary points, and we already discussed in our theory that stationary points are the points where function has maximum or minimum value, and we will get these values by putting our first derivative equal to 0, and from here, or from this equation, we will get the values of x, and in this case we have x is equal to 0. Then put this value in second derivative, which is this one. We have f double dash 0 or second derivative at x is equal to 0 is equal to 0. So that will not help in determining the extreme values, and we will check for first derivative, which is this one. Before x is equal to 0, first derivative is less than 0, and after x is equal to 0, again first derivative is less than 0. So not changing the sign, and we can say this is a value where function has point of inflection. So to find the point of inflection, we will put x is equal to 0 in our given function to get a y coordinate of the point, which is 1. Hence at the last we can say the point of inflection is 0, 1. Now part number 2, f of x is equal to x square minus x minus 2. Repeat the procedure. First derivative is 2x minus 1. Second derivative is 2, because derivative of 1 is 0, and derivative of 2x will be 2. Then put first derivative is equal to 0. This one is actually first derivative. For stationary points, put f first derivative is equal to 0, and first derivative was 2x minus 1, and from here we can say 2x is equal to 1 and x is equal to 1 by 2. So this one is actually a value where function may have a maximum value or minimum value. And to find this extreme value, we will put this value in second derivative and put x is equal to 0 in f double dash x, or second derivative we get second derivative at x is equal to 1 by 2, and second derivative is 2. There is no x, so that will remain a constant number which is 2 and greater than 0. And if second derivative is greater than 0 at this value, then we already know that the given function will have a relative minimum value. So f has relative minima at x is equal to 1 by 2. F has relative minima. Now we will find that minimum value, and to find this minimum value, put x is equal to 1 by 2 in our given function f of x, x square minus x minus 2, and f of 1 by 2 will become, by simplifying this value, we have minus 9 by 4. Say this one is f of 1 by 2 minus 9 by 4, and this is a minimum value of the given function at this value. So minimum value is minus 9 over 4.